All right, a random sample of size 100 is taken from a normal population having a mean of 95 and a standard deviation of 8. A second random sample of size 81 is taken from a different normal population having a mean of 75 and a standard deviation of 9. Find the probability that the sample mean computed from the 100 measurements will exceed the sample mean computed from the 81 measurements by at least 17.6 but less than 20.8. Assume the difference of the means to be measured to the nearest tenth. All right, let's go ahead and get ready to tackle this. So we're talking about a difference of sample means. So let's just go ahead and copy down what we need from before regarding our sample means here. And I'm just going to go ahead and take what we have in this box here. x1 bar minus x2 bar follows a normal distribution with a mean mu1 minus mu2. And then our variance there. So let's go ahead and copy that down. We're going to need that right here. So we need, just remember that we'll have, let's say x1 bar minus x2 bar follows a normal distribution here. Means mu1 minus mu2. And the variance there, sigma 1 squared over n1 and sigma 2 squared over n2 being our variance, okay? And what we're finding out here as we work through these, right, is once I set up these parameters, then these become a typical, well, quote unquote, just area under the curve, normal curve type question, all right? So let's write out what we have here. We're looking at so let me just organize some things here. So we've got two samples. So I'm going to say I have sample 1 here and sample 2. Just to organize my information real quick. So sample 1 has a size of 100. N is equal to 100 here, right? Population, so our mean here has a mean of 95. Sorry. N is 100, mean is 95. Standard deviation of 8. Standard deviation of 8. Sigma here is 8. So that would mean the variance, or sigma squared, is 64, right? Sample 2, we're talking about 81 units with a mean of 75, standard deviation of 9. Okay. And we're looking for the probability that the sample mean computed from the 100 measurements exceeds the sample mean computed from the 81 measurements. We want the probability that x1 bar minus x2 bar exceeds, so this would be greater than, so it's at least 17.6 but less than 20.8. At least 17.6 but less than 20.8. So at least 17, well, let's see here. So I want to be at least 17.6 and less than 20.8, right? And less than 20.8, right? So here's where we have to be careful on this one, because this is explicitly stated here that the difference in means is measured to the nearest tenth. The difference in means is measured to the nearest tenth. So most of the time we'll come across questions here regarding a difference of means, and most of the time we don't get a statement like this. And when you don't have a statement like this, we assume that it's able to be measured to an infinite degree of accuracy. But when you have a statement like this, we're basically saying then that this difference right here becomes discrete. That is a discrete difference measured to the nearest tenth. And so we are now looking at using a normal curve to approximate a discrete problem. And so what we should be looking for here then is we're going to have some continuity correction, if you will. And so to the nearest tenth, let's see here. What do we need to look at rounding for in terms of the nearest tenth? It wants to exceed, let's be careful with our equals here, at least 17.6. So this should be inclusive, but it is less than 20.8, but it is less than 20.8. Okay, so that is strictly less than 20.8. That is not inclusive, okay? So because this is discrete and we can round these to the nearest tenth, think about this. 17.55 would round to the nearest tenth. That would round to 17.6, which should be included. And then 20.8, strictly less than 20.8, then let's see here. 20.75, well, 20.74 would round down here. 20.75, we should include that. Maybe we should not include that. We can write that as 20.74. Usually you subtract a half unit, right? Because the nearest tenth means we're looking at plus or minus a half here. We're looking at plus or minus a half point there. So I'm going to write this as 0.75. So we can see the symmetries there. All right. Now, there's a decent chance that at the end of the day, after we go through all the computation, that these little extra 5 of hundredths there won't make a difference. But this is stated in the question here that it is measured in the nearest tenth. And so that is why that is there. That is what we need to be working on. So let's write out our distribution for x1 bar minus x2 bar then, right? X1 bar minus x2 bar follows a normal distribution then of mu1 minus mu2. So 95 minus 75, that is a difference of 20. 95 minus 75, so that has a mean of 20. This is a normal distribution with a mean of 20. What's the variance going to be? Sigma 1 squared is going to be 8 squared, or 64. So we're talking about 64 over 100, plus sigma 2 squared, that would be 81, over the sample size there, that is 81. So 64 over 100 plus 1, well, that's actually, we can run this through a calculator there. I believe that that is just 1.64, right? Because 81 over 81 is 1. 64 divided by 100 is 0.64. So yeah, that's 1.64. Let's just write out like 1.64 then. And that is our normal distribution. That is our normal distribution. So we are looking at solving this probability right here. That follows this normal distribution. And so now we can go ahead and try to convert to standard normal. Go ahead and try to convert this to a standard normal distribution question. Let's go ahead and work through that then. We're looking for the probability. So we're going to have 17.55 minus 20. Remember, in the terms of way we wrote this out, this is our variance, right? That's our variance. That's our sigma squared. So divided by the square root of 1.64. Standard normal random variable, 20.75 minus 20 over the square root of 1.64. And let's see what these bounds are. 17.55 minus 20 is negative 2.45. And then we're going to divide that by the square root of 1.64. Square root of 1.6. That's negative 1.913. Negative 1.913, which I will round to negative 1.91, so we can look up at our table, which goes to the hundredths place there. And on the right, 20.75 minus 20, that's 0.75. And then that divided by the square root of 1.64, I've got 0.5856, which is going to round to 0.59 if we round that to two places. And so this nice, lengthy, wordy problem boils down to this normal area curve question. And so we can go ahead and try to find that. Remember, we're looking at areas in between. We're going to go ahead and take the area that we want under the curve and subtract the area we don't want. So less than negative 1.91 here. And we go ahead and we can look those values up in the table. At this point, looking these up in the table should be pretty routine. I've got 0.6943. 0.6943. And that is how we can work to execute that. Okay. I'll mention just something to think about here real quick is if we didn't make these continuity corrections right here and right here, that's really just going to change your bounds here a little bit. And so I'm just going to mention here that I want to note that if you do 17.6 minus 20 over the square root of 1.64 divided by the square root of 1.64, that is approximately equal to negative 1.87, negative 1.87. And you compare that with the negative 1.91 that we actually ended up having to use. Negative 1.87 versus negative 1.91. Go to the normal table and look and compare. Negative 1.87, 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, I believe is right there. Negative 1.87, yep. And negative 1.91 here, negative 1.901 here is right there. So we're talking about difference from 0.0274 to 0.0307. 0.0274. It is a less than 1% change. It's a 0.0033 change. That is less than 1%. In fact, that is 0.3 of a percentage change. Not a huge deal in terms of implications per se, really, but a difference nonetheless here. A difference nonetheless. So I encourage you to look out for that statement if you see something that says the difference is only measured to some degree of accuracy, such as the nearest tenth, right? Or the nearest, the nearest unit, right? Then we would employ a continuity correction, much like we did here.